Hello, this is Juliette Marie, and I'm presenting SLAC, a method for automatically learning data augmentation, developed with Michael Herbel, Diane Merlu, and Julien Méral. Data augmentation is known to improve the generalization capabilities of neural networks, provided that a set of transformations is chosen with care. Methods for automatic data augmentation aim at eliminating this manual selection process. Yet, most prior works still rely on strong prior knowledge. Augmentation policies are applied on top of default transformations that are still manually and independently chosen for each dataset. Such approach makes the underlying bi-level optimization problem more simple. In this paper, we present a method for automatically learning data augmentation without leveraging such prior knowledge. Our contributions allow for more stable and better controlled optimization. Automatically learning data augmentation is challenging. In the literature, the problem is often simplified by applying some transformations by default, such as cutout and random crop for CVPR, or random resize crop and color jittering for ImageNet. These default transformations are typically combined with additional learned transformations. Prior works typically learn to optimally sample over a predefined pool of transformations, aiming to sample more often those that allow for the best generalization. A natural question is then, how much can we improve from a policy that uniformly samples over this pool? Well, recently, development showed that combining these default transformations with a single additional one uniformly sampled can give state-of-the-art results. Our proposed method tackles the more challenging setting where no prior knowledge is incorporated in this policy. We start by explaining how the augmentations are modeled through the parameter phi. Given a pool of transformations, SLAC learns which are the most beneficial and how extreme they can be. For example, is the translation useful? By how many pixels should we translate? This gives two parameters, pi and mu. Pi defines the probability distribution over the pool of transformations, given here by the angle of each slice. Mu defines the learned magnitude upper bound for each transformation, given by the radius of each slice. More precisely, the magnitudes are modeled as smoothed uniform distributions. To allow for good generalization, multiple transformations have to be combined. To learn and combine three transformations, SLAC will learn three probability distributions pi0, pi1, pi2, and will independently sample from them, as well as from a common magnitude distribution mu. Such an approach is challenging due to the instabilities inherent to the optimization process and to the approximations made to solve the bi-level problem. If we naively apply standard optimization techniques, we observe that the model usually collapses as illustrated here. This observation motivated our contributions that are the following: a cold start strategy with a periodical reinitialization of a network, coupled with a KR regularization controlling the evolution of a policy phi. To explain these contributions, let's get back to the bi-level problem. A bi-level problem is such that the loss to minimize depends on the optimal solution of another problem. Here, the goal is to solve the upper level problem. Find the augmentation policy that minimizes the validation loss. The loss is evaluated for a network trained using these augmentations. This network is the solution θ star of the lower level problem, which is solved by simply training the network with a given augmentation policy. Once the network is fully trained, we can make one gradient step on the upper level problem. As you can imagine, strictly solving the bi-level problem is prohibitively expensive. Early approaches such as AutoAugment go this way, but most recent approaches approximate the bi-level problem, often with unrolled optimization, which consists in approximating the optimal θ star of phi with only a few gradient steps, and usually only one step. For our methods, we explored how to combine the efficiency of unrolled optimization with the stability of strict bi-level optimization. This leads to our cold start approach. It consists in periodically reinitializing the network. For speed efficiency, the network is not reinitialized randomly. We use weights θ0 obtained from a prior pre-training with a uniform augmentation policy. This approach divides the search into multiple rounds, that are completely independent, except for the augmentation policy file that is passed from one round to the next. Each round starts with a retraining. The network is reinitialized to θ0 and retrained with the latest augmentation policy. This brings us closer to the original bilevel formulation that requires fully retraining the network for each update on phi. From there, we perform a few guidance steps on phi using unrolled optimization, meaning that θ and phi are alternatively updated. For our current estimate θ star to remain good, we do not want to move too much away from the augmentation policy used for retraining. To ensure this, we introduce a KR regularization on the distribution pi. This defines a trust region for the updates around the policy used for retraining. Let's now move to the experimental results with visualizations of the policies learned. Here is a policy learned on Cipher 10. Note the influence of our KR regularization. The distribution does stay quite close to uniform, which is the initial distribution, yet it performs on par with state-of-the-art methods incorporating prior knowledge. It does favor cutout and random crop that are set by default in prior work, and it also discards invert, that is a nocive transformation removed from the pool by trivial augment. Our experiments on domain nets illustrate how the policy stretches and adapts to different domains. You have here policies found for painting and sketch. You can note that some transformations, such as cutout and rotate, remain favored across domains. However, random resize crop is also favored in paintings, whereas it gets a very low probability for sketches. We can imagine that paintings contain information everywhere in the image, while if we extract a square from a sketch, it might just be all white. As a conclusion, automatic data augmentation formulates as a bilevel optimization problem, which is difficult to solve and approximated in practice with, for example, unrolled optimization. This approximation, coupled with the stochasticity of the optimization process, leads to high instability. With SLAC, we propose to approach the bilevel problem with a cold start strategy, coupled with a KR regularization, which allow for more stability and a better control over the optimization process. Compared to the literature, SLAC does not incorporate prior knowledge in the augmentation policy and is the first to model magnitudes as continuous distributions.